Welcome back to the course entitled Symmetry, Stereochemistry and Applications. We will continue from the previous lecture when we were discussing about topicity of various ligands. So, in this lecture we will talk about the topicity of faces. So, in organic molecules, we get many planar groups like C double bond O, C double bond C, C double bond N, etc. And these groups represent prochiral faces. And what we see is that chiral stereoisomers are generated by addition reactions to these groups. So, for example, if we have pH COH and we add methyl magnesium iodide to that, and then do the corresponding hydrolysis, we get pH CHOH CH3, and we generate a chiral center in this molecule, and we generate it as a pair of enantiomers. Therefore, we call this group or this as a prochiral face. If the reaction takes place from the top of this group or from the bottom of the group, it generates two different stereoisomers. So, as just like the different groups which we homotopic, enantiotopic and diastereotopic groups, here also faces can be identified as homotopic, enantiotopic and diastereotopic. So, let us try to first understand what are homotopic faces. Two opposite faces of a group represents homotopic faces if the addition of same reagent to either faces generates same product. Homotopic faces are generally exchangeable by a Cn axis where n is even, say C2. So, if I draw this molecule, which is nothing but formaldehyde. Now, by now you have learned how this representation, what does this representation mean. Here this C double bond O is in the plane of projection and the H atoms are above and below the plane of presentation. So, we have two faces, one is from this side and one is from the other side. So, this formaldehyde, if we do an addition reaction by cyanide group from this side of the face, we would get the product, that is I am adding HCN, the product would be this one. And if we do the reaction from the other side, we would get this as the product. On careful look at these two products, you can easily identify that these two compounds are same compound. So, 1, this product 1 and 2 are same, that is they are homomers. Therefore, in this molecule formaldehyde, the groups, the faces, two faces of formaldehyde are homotopic faces. Let us try to see another example. Let us take the case of trans 2-butene. And if we do addition of bromine to this molecule, this reaction happens through the formation of bromonium ion and we would get the addition product as this one. Or we would get the addition product as this one. So, these two compounds are one and the same. Therefore, the two faces of this CC double bond are homotopic faces. I leave it to you to draw the Fischer projection of these two molecules and identify that these two molecules are one and the same. Similarly, the faces of RC double bond O R like CH3COCH3 or benzophenone, that is PH, CO, PH, etc. and two faces of trans 2-butene are homotopic. Now, let us see how do we identify the enantiotopic faces. The opposite faces of C double bond C, C double bond O, C double bond N, etc., which are exchangeable by sigma plane, that is Sn with n equal to even, are called the enantiotopic faces. Addition reactions of same reagent to either faces generates a pair of enantiomers. So, let us see with one example. We take the example of a ketone with two different groups attached to it. So, if we add hydride from the right hand side using lithium aluminum hydride reagent, our product would be this one. If we do the same reaction from the opposite direction, that is reduction by lithium aluminum hydride, we would get the opposite product. So, here these two compounds 1 and 2, if you look at them carefully, you will see that they are pair of enantiomers. Therefore, these two faces, the left hand side face and the right hand side face of this molecule, are enantiotopic. So, the opposite faces of MECOET are enantiotopic. Let us take one more example. Let us take the case once again of trans 2-butene. If we do the addition of peroxybenzoic acid from the right hand side, we would get, let us draw this in the form of wedge and dash projection for your easy understanding. So, the product that we would get is this one. the epoxide will form in such a way that we will get a pair of enantiomers. These two compounds 1 and 2 are pair of enantiomers. Therefore, what we can see here, in case of 2-butene, when we had done the reaction little while ago using a bromine addition, which I did not mention at that time, is a trans addition reaction. We will see the mechanism of this reaction in a later lecture. This bromine addition being a trans addition reaction, these two phases are homotopic phases, but when we see this reaction, which is a cis addition, therefore, the same pair of phases now turn out to be enantiotopic phases. So, one can say that topicity of phases depends on the nature or mechanism of a reaction. Now, let us try to define the diastereotopic phases. Opposite phases of pi systems like C double bond O, C double bond C, C double bond N, etc. are said to be diastereotopic if on addition of same reagent to either side generates a pair of diastereomers. Remember that diastereotopic phases cannot be interchanged by any symmetry operation. So, let us try to see this with one example. Suppose we take a molecule which already has a chiral center. For this molecule, we are trying to understand the topicity of the faces of this carbonyl group. So, what we are trying to do is to do the same lithium aluminum hydride reduction, assuming that hydride comes from the right hand side. So, in that case, the product is supposed to be this one. But if we do the reaction of reduction from the right hand side by lithium aluminum hydride, what we would get is this product. These two compounds 1 and 2, you can easily understand that they are a pair of diastereomers. Please try to draw the Fisher projection of these two compounds yourself and see that these two are diastereomers. So, these two faces that we are trying to talk about are the diastereomeric faces. We take another example here. And if we try to add HCN to this molecule from this side and from the other side, what we would get are these two compounds. Sorry. Here this compound 1 and compound 2 once again are pair of diastereomers. Therefore, these two faces which we are talking about are diastereotopic faces. So, we can summarize what we have learnt in last couple of lectures. What we can do is we can classify these different groups and faces in 3 different classes like homotopic, enantiotopic and diastereotopic. So, we can easily draw a table and summarize these two lectures. The headings of the table are the following. Criteria of substitution or addition products, criteria of symmetry, and the nature of the ligand or face. So, the first point is, if the products are same, then the ligands exchange position via a CN axis or the faces exchange by C2 axis, then those groups or faces are to be termed as homotopic. Condition number 2, if the products of substitution or addition reactions are a pair of enantiomers, then the ligands or faces are interchangeable by Sn, sigma or I. Then those groups are called enantiotopic groups or enantiotopic faces. The third one is, if the products are a pair of diastereomers. Then the no symmetry can interchange the groups or faces. They are called the diastereotopic groups or faces. In this context, I would like to introduce you to another method of nomenclature of these different groups and faces, or rather the faces. So, this is called in a Re and SI, Re and C designations. So, suppose we are trying to talk about a group C double bond X is connected to two different groups A and B, where X can be carbon, oxygen and nitrogen. So, when we see this group, we first try to identify these groups A, B and X in terms of their priority order. Suppose if X has higher priority over A and A has higher priority over B, then this X is given priority 1, A is given priority 2 and B is given priority 3. So, now if we go from 1 to 2 to 3, we are going in anti-clockwise direction. So, this particular phase, which is from the top of this molecule, is designated as the C phase, and if we draw the molecule in such a way that the opposite face is facing us, that is A here and B there, and then 1 to 2 to 3 is in clockwise direction just like R. So, this phase is called the Re phase. So, let us try to see this with a couple of real examples. Suppose if I look at this molecule, here oxygen having the higher atomic number gets priority 1, carbon here gets priority 2 and hydrogen gets priority 3. So, this particular phase of this molecule is looked as 1 to 2 to 3 in anti-clockwise direction. So, it is a C phase, and the other phase, which is the below phase, can be drawn like this. Again priorities 1, 2 and 3. It is 1 to 2 to 3 is clockwise direction. So, this is the Re phase. If we take the example of a CC double bond, maybe having two carboxylic acid groups in the cis orientation, what we see here now, the priorities are changed. Here carbon gets priority 1 because carbon is then connected to oxygen. This carbon is connected to another carbon, so gets priority 2, and this hydrogen gets priority 3. So, for this particular carbon, this phase is 1 to 2 to 3 is Re. For the other end, this carbon gets priority 1, this gets priority 2 and this gets priority 3. So, here this is 1 to 2 to 3 in anti-clockwise direction. So, it is the SI phase. So, I would like you to see this from a standard textbook and go through further examples and learn it yourself. So, we will conclude this lecture at this point and we will continue from here in the next class.